Okay, hello everyone. So as I said, we've got a couple of odds and ends. And what we like about odds and ends days is that they fortify that which we know. They add little details and nuance to the story of the calculus. Okay? The first question is this: what's a normal line? And we talked about it in class very, very briefly. Daniel shared that he looked it up, and he said, I looked up and I said, what's a normal line? And I Googled it and it said, bing, this is what a normal line is. So what's a normal line? Well, if you have a function and you have a point of tangency, and we know this is called the tangent line, the line normal to the function f of x at x equals x naught is the line that is perpendicular to the tangent line. So this is, right here, this line here is called the line normal to f of x at x equals x naught. Okay, so normal to means, it's going to be a mouthful, means perpendicular to the line tangent. Okay, so this red line is the line perpendicular to the line tangent to f of x at x equals x naught. But what's interesting here is if we call the tangent line, in blue, we know the slope of the tangent line is f prime of x naught. You know that perpendicular lines have what relationship between their slopes, ladies and gentlemen? What is the relationship between the slopes of perpendicular lines? They are negative reciprocals. So if you know the slope of the tangent line at x equals x naught is f prime of x naught, the slope of the normal line here is going to be the negative or the opposite reciprocal, negative 1 over f prime of x naught. Okay? So now we can do all questions involving normal line. Let's see, another little detail. Some notation and terminology. We talked yesterday about this local linear approximation of f of x at x equals x naught. On the surface, this is saying nothing more than the line tangent to f of x at x equals x naught. Well, we talked about the fact that these three words are incredibly descriptive. These three words are suggesting that for values of x local to x naught, so, for values of x close to x naught, the y values of the tangent line approximate the y values of the function. We talked about whether this tangent line is an under or over approximation of the function, and we connected whether or not the tangent line is over or under approximating based on the sign of f double at x naught. Okay, that was yesterday. We also made sure to talk about the fact that who decides who's close enough, right? I mean, this little kind of interval about x naught that I drew here, maybe that's close enough for me, but you always say, no, that's not close enough. We'll talk about what's close enough when we are together. There's an idea called error, and that's a pretty meaty one that I'd like to talk about together, not over a screencast. But let's do this. Let's say we have this line tangent to f of x at x equals x naught, and let's say that I want to use the tangent line to approximate f of x at some value of x close to x naught. In other words, and just for convenience, I'm going to pick that value of x close to x naught. I'll just say, let's do this. Let's say I want to use the tangent line to approximate f of x at some value of x. Let's call this the value of x. Okay? And what I want to do here is, I'm just going to kind of go up. Okay? Now, I think what I'm going to do is undo that and make this space a little bit bigger, strictly for the sake of just clarity when I'm describing. Okay? So let's say I want to go right here. Okay? I'm going to draw this vertical up. Okay, so when we look at taking x naught and we change x naught, right, we're looking at a change in x, we've called this a change in x. You probably call this a change in x in physics. And naturally, when we change in x, we also have an accompanying change in y. But notice here the changes in y are different depending on whether you're looking at the change in y on the function or the change in y of the tangent line. Now, the change in x is the same, right? Whether I'm looking at the function or the tangent line, to get from x equals x naught to this point, the change in x is the same. This is the change in x, or the run of the tangent line. Here's the run of the function. But this change in y distinction is important. And here's some notation. We denote the change in y of the function that corresponds to a change in x as delta x. Okay? But what is then this change in y? This change in y, to specify change in y of the tangent line, we certainly could just write down delta x of the tangent line, but we have a notation for that. That is dy. So dy corresponds to the change in y of the tangent line. Delta y, oh, I just say I wrote an x there, not a y. Delta y is the change in y of the function. Similarly, delta x is the change in x of the function. Delta y, dx is the change in x of the tangent line. And you can see right here that for our purposes, delta x and dx are always equal, right? If, for example, don't write this part down, like if x naught was, say, let's say the point of tangency, x naught was 3, and I was asking you to use the line tangent to f of x to approximate the function at x equals 3.01, right? Whether I look at the tangent line of the function, the change in x is 0.01, so delta x equals dx, right? But dy and delta y don't necessarily equal each other. Notice I said not necessarily. We talked in class yesterday about the fact that if f of x is a linear function, then certainly dy and delta y will equal each other because the local linear approximation of f of x will equal itself, right? But most of the time, we will see that dy and delta y do not equal each other. However, what could you say about this? As delta x, or I can even say dx since they're equal, as delta x or dx approaches 0, in other words, as this interval gets smaller and smaller and smaller, tell me the relationship between dy and delta y. What would you say? Yes, let me look at this here. If I pulled this horizontal distance in closer to the tangent line, do you see how the difference, the distinction, the difference between delta y and dy becomes smaller, right? I can say this. I can say delta y minus dy approaches 0, okay? Or I could say that dy approaches delta y. The point is they approach each other, okay? So one more time, just to make sure we don't lose something here. Notationally, delta y corresponds to the change in y of the function. Dy corresponds to the change in y of the tangent line. All right? Very good. Tonight's homework assignment, you will find some questions where they ask you to find the local linear approximation of some function f of x, right, at, say, x equals -2. And then they'll ask you to use the local linear approximation to approximate f of x at x equals -1.9, right? If the point of tangency is x naught equals -2, and I want to approximate the function using the tangent line at a very, very close value to -2, -1.9, one could argue is close, right? They'll have you use the local linear approximation, but then they're going to ask you to depict graphically what you just did. Label f of x, label the local linear approximation, label dx, dy, delta y, delta x, so on and so forth. Okay? Okay. Moving on. Let's revisit the relationship between f of x and, oh, what does this notation mean, everyone? Yes, that's the inverse of f. That is the inverse of f. And let's recall, let's go way back to the days of early fall. What does it mean for a function to be one-to-one or invertible? Let me put a couple of just quick sketches up here. Okay, I'll do kind of like a generic polynomial function. I'll do, let's see, how about, a nice, let's do like a nice square root function. How about a logarithmic function? How about, let's see, I think, should we do a trigonometric? Sure, let's do a trigonometric function. What function is this, everyone? Okay, what function is this? Yes, it is y equals tan x, right? Okay. Okay. A function is one-to-one if the reflection image of f of x over the line y equals x is also a function. So you may be having to go way back and scratch your brain a little bit. When we talked about the relationship between f of x and its inverse, the relationship between f of x and its inverse graphically is that when you reflect f of x over the line y equals x, the image you get is the inverse of f of x. So I'm going to, let's say, go over here and say, let's take a look at reflecting this curve over the line y equals x, and with reasonable accuracy we get something that looks like this, right? Okay. Here, if I reflect over the line y equals x, I get something that looks like this, correct? Okay. Now look at these two cases here. Do you see how the red, which is the function, so here this is the function f, this is the function f. When I reflect f over the line y equals x, the image over the reflection line y equals x is still a function. If f of x inverse is also a function, we call f of x invertible. Okay? If f of x inverse is also a function, f that is one-to-one or invertible. Look over here. This function f, kind of a generic logarithmic function, asymptote at x equals 0. When I reflect that over the line y equals x, here's its inverse. Notice how its inverse is also a function of x. Therefore, f is invertible. Let's go over here. I'm going to try and reflect this function over the line y equals x. It may help just to give you some body parts. Let's say this root here is at -7. Let's say this root here is at 2. Let's say this root here is at +7. Let's say that this max occurs at, -1, 8. And let's say this y-intercept occurs at 0, 6. Okay? Let's also remember, too, what is the relationship between x and y on the function and x and y on the inverse. You may remember this. X comma y on the function corresponds to y comma x on the inverse. So when I am looking at this point, -7, 0 will become 0, -7, right? 2, 0 will become 0, 2. 7, 0 becomes 0, 7. Okay, -1, 8 becomes 8, -1. And already I can kind of see what's happening here. What is this point? 0, 6 becomes 6, 0. All right, and if I'm pretty good with this, I will have something that looks like, okay, well, my art ability is not that great, but you can see how, with reasonable accuracy, if I take that red function f, fold it over the line y equals x, what I get here is this kind of citron color. The point here is that f is not invertible. F is not one-to-one. The reason why f is not one-to-one is because its inverse is not a function of x. How about tan x? And remember, let's go back in the day here. Tan x, right? If we look at the entirety of the tangent function, which has infinite repetitions of this cycle here, you hopefully recognize that all of these curves, right, that occur along the x-axis, if I reflect the entire tangent function over the line y equals x, what I'm going to get here, okay, are functions of, this is the function of tangent of x's inverse, which is clearly not one-to-one. But you may recall that we talked about in trigonometry, in order to make y equals tan x one-to-one, we just look at a portion of y equals tangent x over the restricted domain negative pi over 2 to pi over 2, right? And if you look at tangent y equals tan x over the interval y equals negative pi over 2 to pi over 2, so this is just y equals tan x over the interval of x from negative pi over 2 to pi over 2, this is one-to-one or invertible, because if I reflect this curve over the line y equals x, these vertical asymptotes become horizontal asymptotes. And what I get is a picture that looks like this. Okay, so when we talked about functions and their inverse back in the day, this is just kind of a brief refresher. We talked about the fact that inverses and their functions graphically are reflection images of one another over the line y equals x. We talked about the fact that a point x comma y on function f corresponds to y comma x on the inverse. And then there was also the algebraic definition, which I'm not going to get into right now on this screencast, but there's an algebraic definition which said this, that the composition, if f of f and its inverse, so if we take f and compose it with its inverse, the special relationship algebraically or analytically between f and its inverse is that if I compose one within the other in either direction, they are always equal, and they are always equal to x, right? This property does not hold if you have two functions that are not inverses of one another. Do you understand? Okay, but if you have two functions that are inverses of one another, each composition equals x. Okay? All right, that was just some kind of background. Let's talk about the calculus then of functions and their inverse. And these are just great questions because they really force you to, again, understand, right? I mean, we can certainly memorize till our heart's content. And there is a formula, so to speak, to memorize with respect to functions and their inverse. But before I show it to you, and I'm not showing it to you in this screencast, I'm going to ask you to think with me. Thinking about something is always easiest. So please go to Packet C, if you will, and please open up to page 7. When you open up to page 7 in Packet C, you're going to be on this screen right here. And let's look at question number 1. Okay, so let f and g be functions that are differentiable everywhere if g is the inverse function of f and g of 3 equals 4 and f prime of 4 equals 3 halves, then g prime of 3 equals, wow, what a mouthful. All right, let's talk it through. So we'll do this first one pretty thoroughly, and you can mark up over here on the side if you want to. But let me ask you this question, ladies and gentlemen. This tells you right here that on function g, there is a point whose ordered pair is 3, 4. Okay, this is on function g. What that tells me then is, since g and f are inverses of each other, there has to be a point on f whose point that corresponds to 3, 4 is 4, 3, right? Now what's interesting is, look, there's a point on f whose x-coordinate is 4, y-coordinate is 3, and then this detail, f prime of 4 equals 3 over 2. This is the slope of the line tangent to function f at the point x equals 4. And don't forget, slope is, right, we can't forget the basics, slope is change in y over change in x. Well, what does this tell you? If this point, 4, 3, corresponds to 3, 4, and the slope on f at x equals 4 is 3 over 2, and 3 is a change in y, 2 is a change in x, then that means g prime of 3, right? The slope of this tangent line should correspond to the slope, the slope described here should correspond to the slope described here, in that x should become y and y should become x. So g prime of 3 would just equal 2/3, right? It's just thinking about it. It's just thinking about it. No formula needed, just thinking about it. Let's go to number 2. Okay, number 2. f of negative 3 is 2, f prime of negative 3 is 3/4. Then, oh, look at this notation. This means f of negative 1, okay, this means the derivative of the inverse of f. This means the derivative of the inverse of f at x equals 2. That notation means, see the deriv right there, the derivative of the inverse of f at x equals 2. Okay, let's do the same thing. Now they just called this the inverse of f instead of giving it a name like function g. But again, let's talk it out. On function f, there is a point whose ordered pair is negative 3, 2. On the inverse of f, that point, negative 3, 2, would necessarily have to correspond to 2, negative 3, right? Well, the slope of the line tangent to function f at x equals negative 3 should certainly correspond to the slope of the line tangent to the inverse at x equals what, everyone? Yes, at x equals 2, which, no surprise, is what we're being asked for. So the slope of the line tangent to f at x equals negative 3, this slope equals 3/4. Well, if the slope at x equals negative 3 is 3/4, what do you think the slope at the corresponding point to negative 3/2, which is 2, negative 3, that should be, again, y becomes x becomes y, 4/3. Boom. Okay? I want you to go ahead and try 3 and 4, just 2 more twists on the same kind of question, and then replay me for the answer. Okay, so let's do number 4 first. Number 3, there was questions, a detail missing from the question, and I'll show you why in a second. But number 4, okay? Number 4, the question is saying f of x equals sine x, and they want you to find the slope of the line tangent to the inverse at x equals radical 3/2. All right, so I went first and looked at the inverse of f and figured out what is the point in question, right? On the inverse of f, the x-coordinate of the point in question is radical 3/2. That means on the function f, if the x-coordinate is radical 3/2, the corresponding point in question on function f has a y-coordinate of radical 3/2. I then went and said, okay, here is function f. What value of x will give me a y value of radical 3/2? In other words, sine of x equals radical 3/2. What is x? You have to remember a little bit of here. For sine x to be invertible, for the inverse of sine to be a function, we only look at the restricted range of angles from negative pi/2 to pi/2. So the question here is, what angle between negative pi/2 and pi/2 has a sine that is radical 3/2? That is pi/3, or 60 degrees, okay? So now I know the point in question on function f is pi/3, radical 3/2. That means that corresponds to the point in question on the inverse, which is radical 3/2, pi/3. So first here I went and worked with f. F prime I know is cos x. F prime at pi/3 is 1/2. That means the derivative of the inverse at the corresponding point, whose x-coordinate is radical 3/2, should be, again, reversal of x over x and y, 2/1 is the answer. Look at question number 3. You may have figured out why it is that this answer can't be answered. There's more information that apparently was not given here. You know, textbooks make errors all the time, but let's talk it through. So this is saying here's f of x equals x cubed minus x plus 2. You're asked to find the slope of the line tangent to the inverse at x equals 2. Similar logic. On the inverse, the point that I'm being asked about has an x coordinate of 2. Don't know the y coordinate, but I do know that on the function, if the x-coordinate on the inverse is 2, 2 is the y-coordinate on the corresponding point on the function. Now here is me using f of x, saying when y equals 2, what will x equal? And when I solve for x here, I get multiple values for x. I would put money, actually I put my entire personal fortune on the fact that what was missing here is a domain restriction on f of x that would make this function invertible, thereby allowing the function to exist. And I bet the domain function is if f of x equals on the interval of x bigger than 0. Okay? So that's what I'm guessing is there. In any case, if we go ahead and adopt this restriction, we would knock out this and this. And the question is, okay, so this point now has an x-coordinate of 1, right? 1 comma 2 on the function corresponds to 2 comma 1 on the inverse, right? And then, I don't know why I scratched this out. And then I said, well, let's take f, find f prime. F prime equals 3x squared minus 1. Let's find f prime at x equals 1. That will equal 2. And this slope, in its relationship to this slope, again, x and y reverse, this value is 1 over 2. Okay? All right, so that should be good to go. Let me give you homework, and homework is going to be from several sources. But what I really like here about this this particular part of our discussion specifically is that this, inverse functions, slope of lines, tangents to inverse functions, it really didn't need any calculus at all. What it needed was really a reminder of what does it mean for a function to have an inverse? What does it mean if you have corresponding points on f and its inverse? And what does then that mean about the relationship between the slopes of the lines tangent at those corresponding points? Let me put your homework up. Okay, here it is. Packet C, please do page 8, all of it. In your calculus textbook, please go to 218, do 37 and 51. And then this last part, I guess it's number 3. In your text, read from the very bottom of page 197, okay, and it's right there in blue. It says, increasing or decreasing functions are one-to-one. I want you to read that, and then read through example 2 on page 197, okay? And then I want you to then do page 201 to 202, numbers 5, 7, and 9. All right? All right, great job, everyone. Goodbye.